Welcome us in the series of videos on topology. This is video number 62 of this course and we are looking about the compact spaces. Okay, and in the last video we have talked about a Lebesgue covering lemma. Let me recall what we have proved. This is what we have done in the last video. Let X. So this statement says if X is sequentially compact matrix space, then for every open cover, say U alpha belongs to I, there exists a delta greater than 0. This delta depends on the open cover, of course, such that if you take any subset A of X with a diameter of A is less than delta, there will be an element of this cover such that A will be a subset of that element, this U alpha A. And we have proved this. Now, this delta which is stated in this lemma is called the Lebesgue number. Okay, this is called Lebesgue number for this cover. So let us write that is the definition. So this is our video number 62, and let us write note delta greater than 0 in above theorem, that is Lebesgue covering lemma. In above theorem is called a Lebesgue number of the given open cover. Okay, so the delta which is greater than 0, which satisfies the given condition and all, that delta is called the Lebesgue number. Okay, and this also you can note, if delta is a Lebesgue number, then you can prove that if you have any number which is less than delta, that also is a Lebesgue number. So if delta greater than 0 is a Lebesgue number, I'll give it a Lebesgue number of an open cover, say V, and if we have any other element, any positive number which is less than delta, and suppose 0 is less than, say, delta 1, which is less than delta, then we can prove that then this delta 1 is also a Lebesgue number. So Lebesgue number is not unique, in short. Okay, so if 10 is a Lebesgue number, then 9 or 8 or 1.1 is also a Lebesgue number. So Lebesgue number is not unique. So from lemma we can write just a corollary for the last theorem we have proved, lemma for all the corollary. If X is compact metric space, then we can say that every open cover, say for X, admits or has a Lebesgue number. This we already proved. Okay, so if we have a compact metric space, then if we have any open cover, then it will have a Lebesgue number. Okay, so let's move ahead now. Let's take a theorem. or let us take on the next page. Theorem. Is also important. We will show that every sequentially compact metric space. Again, this metric space words are very important. Remember that. Okay. So every sequentially compact metric space is complete. So again, we have a new word here, complete. So a complete space means if you have any Cauchy sequence that will be convergent in the space X. Okay, so we have a metric space say X. This is called complete if you take any sequence which is a Cauchy sequence that will be convergent in X. Okay, in that case we can say that X is a complete metric space. Okay. So if you are not aware, please check the definition of Cauchy sequence and some properties of complete metric spaces. So let us move ahead here directly and proof. So we need to show that we assume that X is a sequentially compact metric space and we show that X is complete. So let X be a sequentially compact metric space. So this is our hypothesis. We have taken a space X which is sequentially compact metric space. Okay, we need to show that this is complete. This X is complete, and to show that X is complete, let us take a Cauchy sequence in X, and let Xn be a Cauchy sequence in X. Okay, let us take a Cauchy sequence in X. We need to show that this Xn is convergent in X, and to show that we will use this fact: X is sequentially compact metric space. Okay, so now since by hypothesis, since X is sequentially compact metric space and we have a sequence in X, implies there exists a subsequence, there is a subsequence say X and K of this sequence, original sequence Xn, such that the subsequence X and K is convergent. There is a definition by the definition of sequentially compact metric space. Sequentially compact space. A space X is called sequentially compact if every sequence has a convergent subsequence. So in this case, we have this Xn which is a sequence in X. So this will have a convergent subsequence, and let us take that subsequence as Xn K. Okay. Say convergent such that X and K convergent to say X. That means there is some X in X such that this X and K converges to X. That is X and K converges to X, and this X will belong to X. Okay. Of course, if it converges, then it converges to the unique point. That also a simple fact which we can do. Now, one thing you might have already proved in your real analysis courses, that if Xn is a Cauchy sequence and if there is a subsequence of a Cauchy sequence which is convergent, then the Cauchy sequence is also convergent. Okay, so here we will claim claim that our sequence xn converges to x, this x. Okay, so let's move. And to show that this xn converges to x, let us choose some epsilon greater than 0. Okay, this converges means for epsilon greater than 0, there exists some natural number such that distance between xn and x is less than epsilon for all n greater than or equals to that natural number. That is what we want to prove. So let us take epsilon greater than 0. So let epsilon greater than 0 be some arbitrary positive real number. Okay. Now for this epsilon greater than 0, we need to find some natural number, say n naught, such that distance between xn and x is less than epsilon for all the natural numbers which are greater than or equals to n naught. This is what we want to do now. So let us take this epsilon greater than 0 and use the fact that since this xn is a Cauchy sequence, there exists a natural number, say n1 belonging to natural number such that the distance between, by the definition of Cauchy sequence, the distance between xn and xm, 2 points in the sequence, will be less than, let us take epsilon by 2 for all m and n greater than or equals to n1. Okay, so what we have done, we have taken this epsilon greater than 0, we kept it aside. Now we choose epsilon by 2 which is greater than 0, and for this epsilon by 2 which is greater than 0, there exists some natural number such that distance between xn and xm is less than epsilon by 2. So this is our new epsilon for which we will use the definition of Cauchy sequence. Okay, don't get confused with it. Okay, and secondly, let me just erase this. Now secondly, we have subsequence which converges, right? Since we also know that the subsequence x and k converges to x, right? So again, for epsilon greater than 0, say for epsilon by 2 greater than 0, there exists another natural number, say n2 belonging to natural number. This n1 and n2 may be different, may be same, we don't know. Okay, so there exists n2 greater than n2 belongs to natural number such that distance between x and k and x is less than epsilon by 2 for all k greater than or equals to n2. Let us choose the maximum one. So let us choose, say, n naught, which is equals to maximum of both the natural numbers, n1 and n2. Right? So this will be true for all m and n greater than or equals to n naught, and also this will be true for all m and n greater than or equals to n naught, because we are taking the maximum one. Okay, so for all n greater than or equals to n naught, this we can say that the distance between xn and x by triangle inequality, as we have used in the last proof, distance between xn and x is less than distance between xn and x capital N naught plus distance between x and naught and x. Now this is less than epsilon by 2. This is also less than epsilon by 2. So this is less than epsilon by 2 plus epsilon by 2, and altogether this will be equals to epsilon. That is, what we have proved is distance between xn and x is less than epsilon for all n greater than or equals to n naught. Okay, and hence Hence, our sequence xn converges to x, and hence x is complete. So what we have done is we have taken a Cauchy sequence and we showed that this Cauchy sequence is convergent. And if that is the case, we can say that X is complete matrix space. Okay. So whatever we have proved till now, we can use here in a corollary, and we can say that every compact matrix space is complete. Why? Let me write it as a corollary. Just 2-3 statements. Corollary: every compact matrix space is complete. Every compact matrix space is complete. Okay. Why? Use the previous knowledge what we have. We proved that every compact space is limit point compact. We proved that every limit point compact matrix space is sequentially compact. And just now we proved that every sequentially compact matrix space is complete. Right? Here we have proved that every sequentially compact matrix space is complete. So if we use these 3-4 statements, then we will show that we have proved that every compact matrix space is complete. Okay? So let me write, let X be compact matrix space. So if X is compact matrix space, this implies X is limit point compact. Right? We have proved this limit point compact matrix space. And if X is limit point compact matrix space, we also proved that X is sequentially compact matrix space. Sequentially compact matrix space. And just now we have proved that if X is sequentially compact matrix space, then X is complete. And we are done. Right? We have proved that every compact matrix space is complete. Okay. So this is all about what we have proved here. So in the next video, we will talk about totally bounded spaces. Okay. So stay tuned and stay safe.